Good morning. In this video, I would like to explain what using IoT signals in a radar means, how we can use it on augmented reality glasses, and how all of this relates to the so-called Internet of Things, device template or device sectors. Now let's have a look at the slide to see the terms we utilize and their respective meanings. The very first term we'll discuss is a site. Site actually refers to a physical location, such as a hall or a branch, belonging to a particular company or organization. And within such a hall, there exist sectors or rooms. These can either be distinct sections of the hall or complete rooms in their own right. In each room, we possess a specific quantity of devices that are situated in that particular area. And these devices, commonly known as devices, are constructed based on device templates. Device template is similar to a class of devices. Therefore, if we possess an identical device but it is situated in 5 distinct locations, we would have a single device template for a robotic arm, such as the Fanuc, and subsequently, we would have specific robots that belong to this particular type. This is the difference between device templates and devices. Our configurations, such as IoT signals, or what nodes we have connected, or hints, are based on so-called device templates. There we connect it once and then all machines of this type will be properly connected. In this demo, we have exhibited IoT signals, which function as an additional device template. I have the ability to connect IoT signals, which you will have the opportunity to see at a later point in time. These signals are simply calls made to REST APIs of different systems. This could be Azure, IoT, or any other signals, for example. And here we will also talk about how often we refresh. An additional interesting aspect to our tutorials and devices is the nodes. We use nodes for this purpose because if parts of the machine are in different places, they may be slightly shifted, or even a more advanced example like the robotic arm, which has the ability to move and is securely locked in a predetermined position, allows us to obtain the current position by leveraging IoT signals. This enables us to accurately display the arm's location on the device, providing real-time visual feedback during tutorials conducted in the exact physical space where the arm is positioned at that moment. Let's see at the bottom on our platform. We first enter the device template, and here we see one device template Hamlet. What does it look like in reality? We are standing in front of some CMC machine, and using HoloLens or similar devices, we see information and can spatially, i.e., so-called unique comprehension, positioning our signals. And in this location, we possess signals of the Internet of Things, IoT type. Here we see some information that is displayed in the right place, and in this way, in a simple way, we create it all. Now, how to include such IoT signals? On the IDLE platform, we can manage signals. Actually, each signal is a request to a RESTful API, where signals from the Internet of Things are logged. We have the option to enter the sandbox in order to check and verify the current value of such a signal. Here, in this case, we have one signal, and it is called signal A5 here, which can go through a certain connector using a post. At this moment, it is Azure IoT. And issue the appropriate query. Here we see the SQL statement. That's how Azure queries Azure IoT for some information. And we can say that we want to have this information returned as JSON, technically speaking. And what comes from this query we can use later in our formula that defines how our IoT signal looks like. At present, we have already recorded it. Here we have 3 output variables, and we can utilize them for our purposes. If we edit this signal now, we are saying that this is signal A5, which we mentioned, and here we can also specify what maximum values it should take if it is above 31, what lesson should we show, as a way to solve the problem that is associated with such a signal, whether it is predictive maintenance or a local signal. Let's see what else we can do here. Of course, we translate all these signals. We can change the description of such a signal here. We can also tag such signals to make it easier to filter them. In a moment, we will change this name, record it, and it will be appropriately available in the system then. Of course, for each signal, we can also change the icon under which it will be displayed. Here we add a new signal, As I mentioned before, it can be done using a nut, bolt, or similar methods. In addition to signals, we also possess hints. Hints are similar to 3D pointers, indicating a specific location where something is positioned. And now let's move on to the next topic, sectors. Here we see the sectors, and they can also be shown geologically. Here we see what would be in our area. And in a moment we will enter such a room which has been defined, and we calibrate ourselves there. How does it look like here on HoloLens, for example? We have our calibration points. We need 2 calibration points, a calibration photo, and here we see that one of the calibration points, usually we look for very characteristic points, is right here on these doors on the flap, a location that will not change position within a designated room. The same applies to the second point. We can, of course, verify it in the photograph to observe its appearance, to obtain precise information, and we observe that the second one is located directly next to the signal reader used for accessing this room. As we marked it at this moment, the system knows where we are and marks it there, in the cube, in the block, where our device template will actually be. Here we can see that there are 2 device templates. We select one and it shows us which lessons are associated with this template. And this is how it appears on our backend. So this device template contains some IoT signals that we observed at the bottom, and it possesses nodes. We will pass the nodes in a moment. Nodes are information about the moving elements of a given machine. In this specific situation, it does not have to be a robot. It can be a console that stands next to it, and that is why the presence of dynamic space is required. And here we observe that we have one lesson attached, and we are simply transitioning to this lesson. Of course, there can be a lot of these lessons. And here we have a lesson where it was created on HoloLens or Quests 3s because we have passed through, and here we go step by step through the whole lesson. Depending on that, what is important is, for example, 3D model, where we show, and it can be with photogrammetry, which is a very cheap version of creating a 3D model, where it is in space at all. We can also give ourselves tips in this space, or generate an audio file that will be automatically read so that we actually have free hands and don't have to read by hand where it is located at all. We also generate a PDF due to an audit, because it needs to be printed, to have an audit of what happened. It is liked in every language. Of course, we have a table of contents for our entire manual. Now let's see what sub-elements we have. We can also edit each point. Not only on HoloLens or glasses, we can enter here and change the text. We also create audio recordings that can be converted into written text using a transcription service. And now that we have already made the instruction in English, we can automatically transport it, automatically translate it into German using DeepL. At this point, we already have an example translation available. The quality of the translation is quite impressive. And in just a moment, we will proceed to take another step, which involves generating a brand new and authentic translation. This new translation will be more akin to a descriptive text rather than a straightforward translation, providing a more detailed and comprehensive understanding of the content. And just a moment.
Schrauben Sie den Adapter mit kurzen Schrauben und einem Inbusschlüssel Größe 10 fest auf das Gerät und setzen Sie ihn ab.
Using short screws and a size 10 Allen wrench, screw the adapter firmly onto the vise.
And now when we switch, we can see these translations in any language we want. Here it is in German and in English. It is available in both languages, German and English. A straightforward approach to creating instructions. We do not really need just photogrammetry or a specific 3D model, as we already have the possibility and can utilize it with smartphones, advanced HoloLens, or Quests, providing us with a range of options for implementation. We can also add hints to each point on the web. Here, for example, we add a place in 3D where it should be. We have the ability to alter the perspective from which this is presently being displayed. We have the capability to add supplementary annotations, such as a circle indicating that this is of particular significance or comparable data. And we document all of this, and at this particular moment our instruction is updated. Naturally, we also possess a publishing model, which means that if I make changes here, and they have not been accepted yet, they are only visible to the editors of this content, not to everyone else who may access it. I can additionally include a photo from the local hard drive, as well as an operation scheme, which is required in this particular case. And here we won't record it at this moment because we actually want to leave our demo as it is, but of course after recording it would be immediately available for all editors.